Oh, there we go. Okay. So now I've got those running. So thank you very much indeed for the chance to come and talk to you about Project FRESSON, which is a project to design, install, test a hydrogen fuel cell powered electric propulsion system into a Britten-Norman Islander at its first phase. And the name of the project is important actually because the name Project FRESSON, that's named after Captain Ted Fresson, OBE, who was a Scottish aviation pioneer. He set up Highland Airways and inaugurated the first passenger services between Inverness, Wick and Kirkwall in 1933. And we chose that name for FRESSON because, as you'll see later, the aeroplane we are designing and the propulsion system we're fitting in the aeroplane is very well suited to short island hopping type routes in the kind of environment that Ted Fresson set up the services. So what I plan to go through tonight is give you an insight initially into Cranfield Aerospace Solutions, so you can understand where I'm coming from and what we as Cranfield Aerospace Solutions are and what we're doing. Then talk about the mission of Project FRESSON and the team that's been formed to fulfil that mission. Then the aircraft, because this is all about a conversion of propulsion system for an island, Britten-Norman Islander. So why do we choose the Islander? And then why have we chosen hydrogen fuel cells as the basis of our propulsion system? Because that was a very involved and detailed process to get to that. There's a rational reason why we chose hydrogen fuel cells. Then talk about the FRESSON concept in terms of outline, what we're doing, what the propulsion system includes, and our concept for conversion of the aeroplane. And the key requirements were set for that. And then the design challenges that stem from those key requirements have been set. And then what that means, particularly in terms of aircraft level systems engineering, the learning we're developing from that. So why is it difficult and what are we learning? And then how that then gives us a foundation for our allude to. We've got very ambitious plans as Cranfield Aerospace Solutions for the future, built on this first phase of Project FRESSON and on that strategy in terms of our sustainable aircraft roadmap. So in terms of the first one to situate in terms of what Cranfield Aerospace Solutions is, we're effectively a spin out from Cranfield University, but we're 30 years old as a spin out from the university, and we weren't spun out with particular intellectual property, we were spun out as a capability. So we were still on the Cranfield campus, and we share a common owner in terms of Cranfield Group Holdings, but we're commercially separate, so I'm an employee of the company rather than of the university. And we sometimes do work on a commercial basis for the university and likewise, but we're a separate company. And we see ourselves as being uniquely capable for a very small company in terms of our capabilities. So we've retained all the skills and the approvals to do effectively designs of any modification to any aeroplane. We can still do whole aircraft conceptual design, and we're building the capability to restore whole aircraft design in itself. And for that purpose, we retain UK CAA design approvals, or UK CAA Part 21J design organisation. We're also a CAA Part 21G production organisation, so we can make parts and modification kits, and also Part 145 maintenance organisation. And the kind of business we do, particularly in the engineering part of the business, my part of Cranfield Aerospace Solutions, spans 5 broad areas. So R&D type prototypes. So the big OEMs come to us to do the very quick R&D type prototypes, either for a flying test article, a ground test article as a facsimile for flying test bed, or as a subsystem for a big test or R&D program. We do major modifications. So we can do any modification to any aeroplane. So recently, when the university bought a new flying classroom aeroplane, we did all the modifications to turn the aircraft into a flying classroom. We do post-design services, and that includes things like providing structural integrity advice to the Royal Air Force for the Battle of Britain Memorial Flight Spitfires and Hurricanes. So that is the indication of a variety of things we do. We do consultancy and some flight test instrumentation. And it's particularly in our R&D programs that in the recent years, we've been sought out by the biggest OEMs in the business, the Boeings, the GKNs, the Airbuses, Rolls Royces, to do parts of their R&D prototypes. And it's built as a reputation and a capability in things like novel prototypes, novel systems, more electric aircraft, low emissions propulsion. And that's good business and good learning for us. But what it means is our business has been at the whim of the discretionary spend of those big companies. And when times are hard during COVID, we're the people who feel the effect of that when big companies cut their R&D budgets. So 2 or 3 years ago, we took a strategic decision for the company to take that reputation, those skills, what we're learning, and move from being a project-based company doing work for customers to transition over several years to become a product-based company where we bring our own products to market. And FRESSON, which I'm going to describe, is effectively the core of that strategy in our transition from project to product. And so our vision we've set ourselves is to be recognised as a leading integrator of cutting-edge technology for safe, sustainable aviation. And it's the sustainable aviation that's the theme of FRESSON. So in summary, whether we've got the design, production and maintenance approvals, a systems engineering approach that allows us to apply to any technology to any problem. We're committed to decarbonisation, and we've got clear, ambitious plans in terms of delivering certified zero emissions aviation into civil passenger flight. So that leads us to Project FRESSON, and that's when this is the first phase of Project FRESSON for us. And Project FRESSON is about designing, installing and testing a hydrogen fuel cell powered electric propulsion system into a Britten-Norman Islander. And the mission of the project is to deliver the world's first certified passenger carrying truly zero emissions flight. So it's a big mission now. That's where our heading is: zero emissions passenger carrying flight. To deliver that mission, we're a consortium, a very strong consortium made up of excellent UK companies. So for the first phase of FRESSON, which is a flying demonstrator, so we'll fly a flying demonstrator in 2023. That's part government funded, 50% government funded by the Aerospace Technology Institute and 50% private venture funded. And on the team for FRESSON 1, that demonstration in 2023, but also probably going with us on the journey to certified products in 2025, we've got a really strong consortium. So our friends and colleagues in Britten-Norman are part of that consortium, and they're important because that gives us access to the OEM's understanding of the aeroplane and the OEM's data. So Britten-Norman are working with us on this project, and that's key to us. The next part of the consortium is Ricardo, so an internationally renowned engineering consultancy with great expertise in automotive and rail, and they bring to the consortium the expertise in hydrogen fuel cell systems. So the hydrogen fuel cell system, which is the fuel cell stacks and associated balancer plant, as a subsystem of our FRESSON propulsion system, has been designed by Ricardo, and it's excellent to have them as part of the consortium. They're first-rate engineers. We like working with them. Third member of the consortium is almost at the other end of the spectrum in terms of size and time in the industry, is Inverness Tech, which is a small Scottish startup, handful of people, but they bring to the consortium their expertise in manufacturing composite material pressure vessels. So to store the hydrogen that's going to fuel our hydrogen fuel cell system, that's stored as gaseous hydrogen. We need a mass efficient, very high pressure tank to do that. And Inverness Tech are bringing some innovative manufacturing technology to that, and will give us the tanks that we need for our demonstrator and then ultimately for our product. Then reaction engines are part of the consortium as well. So I'll explain later. Hydrogen fuel cell systems bring with them particular challenges in terms of thermal management. So we needed the best possible heat exchanger, the world's best heat exchanger, to deliver that at an acceptable mass and acceptable drag. And the people to do it are reaction engines. Again, we're delighted to be working with people of that quality, and that works very well for both of us, because we, as Cranfield Aerospace and as FRESSON, we need the world's best heat exchanger, and reaction engines were looking for an opportunity to take their technology and make it certifiable for aviation. So by going together on that journey, we both get the benefit out of it. And of course, we're on the Cranfield campus. We're share a common home with Cranfield University, so Cranfield University themselves are participating and giving us access particularly to performance and control modelling and other modelling type services. So that's the consortium, all unified behind that vision of delivering the world's first truly green passenger carrying airline services based around hydrogen fuel cell propulsion. So that's all going to be fitted into an Islander. The question is, why choose the Islander? Why put a 21st century propulsion system into a non-21st century aeroplane in the nicest sense? Well, it's a very successful aeroplane. It's in terms of engineering suitability, it's just right for us in terms of it's about the right power that we need to do. I'll talk about power later on. It gives us about the right available mass in the aeroplane and real estate or packaging volume in the aeroplane that we can fit our propulsion system in there. So from an engineering point of view, it's right. And also from an engineering strategy, it's the right thing to do, because we faced a choice. Do we go straight to a whole new design of zero emissions aircraft, clean sheet design, or do we do the difficult bit, the zero emissions propulsion system in an established aircraft, learn and develop that zero emissions propulsion system, and then make it scalable and modular, and later apply it to a whole new aircraft design. And you see we've adopted the latter approach. So we'll do the propulsion system first, then we'll apply it to other aeroplanes later. So having an existing aeroplane was good for us. And then in terms of the commercial strategy, as I mentioned, we'll fly a flying demonstrator under permit to fly in 2023. Then we'll do a design iteration and fly a product in terms of modification certified as a supplemental type certificate as an STC in 2025, and we'll take that to market. So working in conjunction with Britten-Norman, we'll offer that as a retrofit modification to current Islander operators, or it could be applied through Britten-Norman's aircraft refurbishment and reselling programme, or it could be offered as a modification for new build Islanders, so it breathes new life into the Islander product. And that is a big enough business for us to make it a commercial business for us as we move to being a product-based business, because the market is out there. And that'll be for existing Islander operators. It'll be for operators of other aircraft of a similar size who need a zero emission solution when their hydrocarbon fueled aircraft are legislated out of existence at some point. And it'll also probably have conquesting markets where operators disaggregate their large routes and larger airplanes into potentially smaller aircraft if they're available with a zero emissions propulsion system. So that's why the Islander. And then the big thing is, why did we go for hydrogen fuel cells? Why not batteries? Why not some other system? And this was a process of several months of clinical engineering assessment, properly thorough mission analysis based on the competing technologies. So we took a number of use cases from various potential and current Islander operators and generated some reference mission sets in terms of mission profiles, so durations, ranges, cruise altitudes, generally 3 or 4 key missions that an Islander type aircraft performs. We then generated a number of different propulsion system concepts to test against those mission sets. And they are based largely around, we looked at battery only initially, but battery only doesn't give you sufficient range either for the Islander type use case. So that very quickly ruled itself out. And then we looked at hybrid electric type propulsion systems. So something with an engine driving a generator, either to top up a battery or to use it in a hybrid sense, a bit like in a motor vehicle. And we looked at gas turbine driven generators, piston engine driven generators as well, in either 1 or 2 generators per aircraft, so single range extender or double range extender. And we also compared it with hydrogen fuel cell as a means of generating electrical power to drive the motors. And we ask ourselves 3 key questions. First key question is, can it be better than the existing baseline aircraft? So the Islander BN2B26, 260 horsepower Lycoming engines, gas fueled. Can it be better than that aircraft in terms of cost per passenger on each of those reference missions, and also emissions per passenger on each of those reference missions? And we did it per passenger because that took into account the mass differences of the different systems as well. So can it be better than the existing aeroplane? Can it be better than the alternative that the market already has, which is if you operate an Islander with piston engines using avgas, which is expensive and difficult to get, you could buy a turbine Islander running off avtur and straight away exploit the cheaper fuel. So can what we offer be better than that? And what is the optimum amongst those those propulsion systems? We took into account some special factors as well. So particularly with the hybrid electric propulsion systems, the benefit you get from a hybrid electric having a battery in the system as part of the energy storage on the aeroplane, you only get that if you then use that battery for a significant proportion of the mission, in terms of using less hydrocarbon fuel and bringing the cost down. And to use a battery that's viable to fly on an Islander, so something less than half a tonne of battery, that means you've got to pitch that solution at very, very short legs, very, very short flights to get a significant portion of that flight as under battery power. Otherwise, you're flying a half-ton battery around for nothing. You're carrying that extra weight and you're not getting the benefit from it. What that means, though, is you're limited to the very short flights and then recharging between each flight, recharging very quickly and very frequently. And we found actually that means if you have a battery-based system, that can bring the battery life down from over 2 years to something like 6 months. So we're talking about Islander operators changing a half-ton battery pack every 6 months, which is economically unviable. So that's the Achilles heel of battery-based systems, particularly hybrid electric systems in this case. And we also asked ourselves, where are the differences in terms of operational flexibility and restrictions between having a hybrid concept based around a single range extender, so a single engine driving the generators to charge the batteries to drive two propellers, or dual. And actually, if you have a single range extender, but as in driving the generator, you effectively give yourself a single engine aeroplane, even though it's still got two propellers and have single engine operating restrictions, which again, particularly outside North America, doesn't work in terms of the operating restriction on the aeroplane, what we need to do. And we also made some technology assumptions. So we had to look at where we thought technology will be for 2023 for our demonstrator, and where it's going to be beyond 2025 and beyond. And those key technology assumptions are largely around the batteries, the battery-based systems, in terms of their energy density, so kilowatt hours per kilogram, and their power density, so kilowatts per kilogram. And here we found some interesting facts and reality, I think, and maybe battery experts will challenge me, but when we're looking at battery figures, the headline battery figure has to be interpreted and understood correctly, because it's often published as a start of life figure. But because this is for an aircraft product, we need to consider the end of life figure. So the power or energy that battery will provide in its last flying hour before it's either refurbished or replaced. So it's a rated figure at end of life is what's important for a start. The next thing is that battery figures are often quoted at individual cell level. So something like an AA battery, that's an individual cell in battery terms. Often quoted at the individual cell level. When you aggregate those up to the modules that actually make up the batteries, and then into a whole battery pack, you start to add a lot of parasitic weight in terms of the structure of those modules and packs, and their cooling systems and their interconnections. So then those real energy densities per kilogram start to drop a lot from headline figures. So we had to feed that into the analysis. And then what was also key in the analysis was what's the specific power of the hydrogen fuel cell system. So its peak output power, electric power over its total mass, and similar for the electric propulsion unit. So it's power to weight ratio or specific power. And we took some industry informed sensible assumptions about where we could be today and in the future. And actually we came up with some key findings which are important. So hybrid electric is only competitive on very short legs, but that's got an unacceptable penalty on battery life. So that doesn't really work. The only benefit you get in fuel costs is if it allows you to swap avgas for avtur by having a gas turbine range extender. But you could do that anyway by buying a turbine islander instead of a piston engine islander. Hybrid electric, as I mentioned, is only competitive on short legs, but then the battery life doesn't work. So you're swapping out a very expensive battery pack too frequently. But hydrogen, even with sensible assumptions for where it can be today, tomorrow and in the future, was competitive in terms of lowest energy costs, because hydrogen, we can project hydrogen prices coming down. You don't need a very high mass of hydrogen to fly this kind of airplane versus increasing costs for avgas and avtur. So it's competitive on price, and will become ever more so, and potentially will become the only fuel that's acceptable, other than synthetic aviation fuels, but also it's zero tailpipe emissions, which hybrid electric can't offer. And it's zero tailpipe emissions. It can actually be completely net zero if the hydrogen itself is produced with an electrolyser on the ground, run from surplus renewable energy, and that's the vision. So it's free energy in a way. An engineer can't have free energy, but it's free economically. So hydrogen was the answer for us. And when we discussed this with our colleagues in Britten-Norman, they went, we agree. We didn't see a future in battery or hybrid electric, but we actually think this is the way to go for this aircraft. So that was the why hydrogen. And so that leads us to the FRESSON concept. So we said, let's take a baseline islander and let's make sure we maintain the baseline aircraft's takeoff and landing performance, because it's a STOL aircraft. That's the unique selling point of the islander. That's why the operators use it. We also said, let's keep the climb and cruise performance the same for similar reasons. Let's define a practical endurance and fuel reserve. But we know with hydrogen fuel cells, I'll explain later, we can't get the amount of fuel onto the aircraft as we can with avgas or avtur. We can't do that, but we can at least define something that is realistic. So our baseline assumption initially was an hour's planned endurance and 45-minute reserve. That hour's planned endurance is a lot less than a baseline islander can achieve, but it still covers 80% of the use case of islanders, so it's still okay. We set ourselves a goal to keep the maximum takeoff mass the same, because we didn't want to do any large structural modifications to the aeroplane, and we don't want to get into the death spiral of heavier aircraft, more power, more fuel consumption, and move away from the optimised point for the aeroplane, and also maintain the cabin and volume so we can keep passenger space because it's a revenue earning aeroplane. So we set ourselves that as the concept, and then the idea was, well, how do we do it? And it's very easy to say in summary. So the concept is based around, we remove both piston engines from the aeroplane. So remove and discard or sell off those two piston engines. We remove the conventional liquid fuel system completely. And then in each nacelle, we fit an electric propulsion unit. And the electric propulsion unit in this terms is the electric motor and the inverter controllers that run that motor and do the power conversion. So that's the EPU for us, installed in the nacelle to drive a conventional propeller. Then in the same nacelle, we fit the hydrogen fuel cell system itself, which is generating the motive power to drive that, to power that EPU. And the hydrogen fuel cell system is the hydrogen fuel cell stacks themselves. So they're doing the electrochemical process to take air and hydrogen in and produce electricity and water vapour out. So that's the generator fuel cell stacks. The fuel cell stacks need a set assortment of compressors and pumps and humidifiers and intercoolers and filters, which is termed balance of plant in the industry. So it's stacks plus their balance of plant plus also the control system. And that together we term hydrogen fuel cell system, and similarly we install that in the nacelle. And to give you an idea of powers, the hydrogen fuel cell system in each nacelle will give us a peak net output power for propulsion of 240 kilowatts, and that will drive an electric propulsion unit that will give us a shaft output power of 220 kilowatts, which is just under 300 horsepower. So what we're doing is installing 300 horsepower of propulsive power, shaft power, to replace the 260 horsepower engines that have been removed. That gives us a bit to overcome the extra drag on the aeroplane that we introduced with coolers and fuel tanks. So each nacelle set replaces the engine, hydrogen fuel cell system and the EPU. Then the the HFCS themselves are powered by gaseous hydrogen, and they come from tanks. So they are undoing tanks probably on the product, or if the demonstrator they're internal to the fuselage for other reasons. So we're storing the fuel in gaseous form at 350 bar for our demonstrator and 700 bar for our product. Now they say extremely high pressures, make the tanks very heavy, but they're standard automotive pressures. So they're already being used in the hydrogen fuel cell industry. And that is effective as a system in terms of the concept. In more detail, and in this audience, I hesitate to put up an architecture diagram that looks as basic as this, but I can't show you all the architectures because it's got Cranfield IP in there. It's somewhat more complicated than this. Again, this is reiterating what I was saying. So if you imagine this is a left-right symmetrical system, imagine the centre line of the aeroplane across the middle of this slide horizontally. You've got the hydrogen fuel tanks storing the gaseous fuel, feeding the gaseous hydrogen to the hydrogen fuel cell systems. Hydrogen fuel cell systems generate the electrical power, and that electrical power is the propulsive power for the aeroplane, the 240 kilowatts, but it's also driving the power to drive its own pumps and compressors, and it's also providing a small amount of power for us to convert to 28 volts DC to operate the existing aircraft systems, because we're replacing, in effect, the engine-driven generators that we threw away when we took the lighting engines out. And then they're driving the electric propulsion unit. To make that all work together, the diamond in the middle is the integrating parts. So we've got a power distribution system doing all those electrical conversions, that electrical control, and the interface with the existing aircraft 28 volt systems. We've also got new controls. So if you imagine the pilot's throttle box in an Islander is 2 throttle levers, 2 RPM levers and 2 mixture levers. We're retaining the current throttle levers, but instead of in the same quadrant with the same intuitive operation, but instead of being throttle levers for piston engine, they become power demand levers. But similarly, they operate in the same manner. The RPM levers we're keeping because we're going to continue to drive a conventional variable pitch propeller, and then the mixture levers are redundant, but we're probably going to use them as an emergency shut off for the fuel as part of the pilot controls. So we adapt the flying controls of the aircraft. And then the other area that we change it and modify is displays. So we discard the conventional engine instruments, so RPMs and pressure gauges, they go. And we replace them with 2 multifunction displays that provide the propulsion system instrumentation. So that's indication of output power, demand versus supplied, voltage on key elements of the system, and also the hydrogen fuel contents. And hydrogen fuel contents is different because we're no longer measuring liquid levels in liquid tanks with either float gauges or capacitive tank units. We're inferring our fuel mass by measuring pressure and temperature in the tanks. So that's different as well. So there's some adaptation, but that's in outline. I can't show you more detail because the way we're doing the power distribution is unique to us, and we've got some innovation in there. So that's the architecture. The key requirements which we are covering, some of them you'd expect anyway. So in airworthiness and certification terms, and therefore safety, that's the top of the requirements list. So as I say, for the demonstrator, fine demonstrator, will fly next year, 2023, and that will be flown under a permit to fly, supported by flight conditions and appropriate safety case. And then in 2025, after further design iteration, we'll fly a product, the retrofit modification, with that system to fit to an existing Islander, under a supplemental type certificate as a major and significant modification. So it's major and significant, so I have to go through the CAA for this, but it retains the existing type certificate, and that's been agreed with the CAA. So our product is a modification. As I say, we've set ourselves a requirement of maintaining the Islander's stall performance, and we have to meet single engine inoperative climb requirements as well. We're keeping maximum takeoff mass, maximum landing mass within current limits, so we don't have to embark on huge modifications to the structure or depart from the optimum position of the aeroplane. We're keeping the zero fuel mass will go up because the fuel mass on this aeroplane is a lot less than you'd expect from conventional wisdom from normal liquid fuel. So in terms of fuel mass, for a demonstrator, we're talking about 23 kilograms of fuel total, usable fuel total. So the difference between maximum takeoff mass and maximum zero fuel mass with passengers is only 23 kilos. For a product, we're currently converging on the right amount of fuel for the product, but it'd be something between 34 and 55 kilos of fuel. So fuel mass is a tiny for a hydrogen fuel powered aircraft compared to what you'd be used to in terms of liquid fuel. We need to maintain rapid response because it's a short takeoff and landing aircraft. Our chief test pilot keeps reminding me what happens when he's landing late at night in bad weather on a short island strip and a sheep walks out in front of the airplane on the runway where it lands. We need to protect the capability for the go around, and the pilot needs the kind of responsiveness they're used to from the piston engine. And that is more complicated to achieve in this because it's a very complicated propulsive chain from fuel all the way through to thrust from the propeller. And associated with that, we're trying to limit operating differences to the baseline aeroplane. There's no point bringing a modification to market that's nice and cheap and compelling as a business case if it means tens of thousands of pounds of conversion training for the crew. So we're trying to make it look and feel like a conventional Islander. And most of the other aircraft level requirements, there's several hundred lines, these are all based on maintaining as far as possible the Islander's performance and characteristics. And then we decompose those into system and subsystem requirements. Now, the diagram on the bottom here, I don't intend to go through or intend to read, but it's to give an illustration of how complicated and interconnected and interactive this propulsion system is. It's fundamentally different from having an engine that needs a throttle control and supply fuel, and it's straightforward, we're used to that. So this is, if you imagine the left-hand side, this is this question about responsiveness. That's a step input in thrust demand from the pilot, which might be from 15 to 95% on the go-around case, and the pilot would expect a response in 5 seconds or somewhat less. That's then got to go through a new control system to a hydrogen fuel cell system. It's got to get its balance of plants pulled up, so things like compressors and pumps, accelerated to provide more air and hydrogen into the fuel cell itself, then supply that output power to the EPU, and then the EPU accelerate the propeller. It's complicated in terms of the number of steps in the process, and it's complicated in terms of the dynamics of the HFCS. In our favour, the electric motor is very responsive because you get maximum torque at low power, almost from zero RAeS. So that's one of the areas where our requirements are going to be very carefully written and then trace all the way through the system to make sure we've got something that in the end is viable. And that's probably the area where we need to be most on it in terms of our modelling and testing later in the programme. And then we derive a number of safety requirements down from that, as you'd expect. So in terms of safety and power output and power response, and mass. So we take that, and this is a systems engineering task from an aircraft level set of requirements to a set of requirements for the propulsion system to a set of what we call subsystem requirements. So, for example, for the hydrogen fuel cell system and the EPU, and these requirements documents run into the hundreds of lines, including things like efficiency, because efficiency is fuel consumption, so is range and endurance. And I'll say we're range limited because it's an inherently heavy system, but also efficiency is about heat rejection in the system and adds to our thermal challenges, which I'll mention later. And then packaging volume, because these systems are really quite large. And then also we've got some quite detailed requirements on startup, because the startup sequence for the hydrogen fuel cell system, then to start the EPU, is that bit more complicated than for a piston engine. And for example, we think we need something like a 1.5 kilowatts for 30 to 60 seconds to get the hydrogen fuel cell system up to a self-sustaining situation. And we need to start on the ground, ideally independent of ground power, and clearly an airborne restart if needed. So we've done that systems engineering work, but it's that bit more complicated than we might expect for effectively a change of engine. And that's what's exposed the design challenges. So the why is this difficult is, well, why can't we, mechanical engineer talking electrics here, why can't we just buy some electric motors, buy something that generates electrical power, stick it together, put a throttle on it, put a control on it and make it work? It's more complicated than that, because we find the interacting nature of fitting a propulsion system, novel propulsion system into an aeroplane makes it more complicated. So in terms of mass, these systems are inherently heavier than the systems we're removing. So for example, we're removing about 150 kilograms of engine and fitting well over 200 kilograms of replacement equipment in that nacelle. So they're inherently heavy. As I mentioned, the maximum zero fuel weight is much higher. The actual fuel is a much smaller proportion of the overall mass of the aeroplane. So heavy systems to deal with. We've got to be scrupulous in managing our mass and setting demanding targets of our suppliers. System efficiency is very, very complicated. So it's somewhat more complicated than fuel comes in, engine turns propeller, thrust comes out, because of the number of conversions and the numbers, particularly of not so much sources but sinks of energy through that system. So we've traced that as a budget and through a Sankey diagram that shows the energy flow from input chemical energy to output in terms of kinetic energy of the aeroplane, and every loss and transition of fuel of energy has to be tracked, because we don't have surplus power budget, and it's also then generating waste heat if it's lost power. System responsiveness I've mentioned already, and then thermal management. So thermal management is the Achilles heel of hydrogen fuel cell based propulsion systems. And if you see a hydrogen fuel cell based concept or glossy rendering and it doesn't have big radiators on it, then you should be suspicious, I would suggest. So what this is about is a hydrogen fuel cell system as an energy converter is a similar efficiency to a piston engine, very similar efficiency, but it's high heat and low temperature. So each nacelle set is rejecting at peak something like 300 kilowatts of heat, but at a coolant temperature of only about 80 degrees C. So the delta T between that coolant and the outside air temperature isn't that big in heat exchanger terms. So therefore you need big heat exchangers. It's different in a piston engine because most of that heat goes out as hot exhaust gases, and the hydrogen fuel cell doesn't reject heat in that manner. So we've got a very, very big thermal management problem. When we first looked at this, we said, well, what size radiators would we need to reject that 300 kilowatts per side? And we're talking about a conventional radiator of something over 2 square metres with a 40% increase in drag in the aeroplane, and the aeroplane wouldn't have got off the runway. In fact, it would have struggled to get to the end of the Cranfield runway with that amount of drag on it. So that doesn't work. So we have to go for an advanced solution. That's where reaction engines come in, because we expressed a target performance for our cooling system as an equivalent mass figure in terms of a combination of mass, a factor on the drag that it incurs, and also any power, although reaction engine systems is unpowered. And they're the only people who could give us a system that was viable for us with their advanced heat exchanger technology, which is spiral arranged microtubes as a spin out of technology from the Sabre rocket program or Sabre engine program. So thermal management is a big thing. We've solved it. We've got a solution for the demonstrator, and we know how we're going to develop it as another design step for our product. Drag then comes with the issue because also we've got cooling drag because we've got new heat exchangers on there. And also we are going to put external tanks in the aircraft. And that's why we've had a hike in the installed power that we're putting in terms of the shaft power of the motor replacing the engine, because we want to maintain the performance of the aircraft. Power electrics is complicated because we're talking at very high power and, for aircraft terms, high voltage. So I won't quote exact figures, but we're talking about voltages in the order of between 500 and 1,000 volts, let's say DC, as our highest voltage, and very high power. So there's potentially a lot of voltage conversions in there across that electrical chain, from fuel cell stacks, electrical power output, to the motor windings. And availability of components that can handle that and be safe for aerospace and be small enough to package and light enough and not give out even more heat is really challenging. Reprovision of conventional systems has been a bit of a challenge. So I've mentioned we've had to reprovision for the engine-driven generators by taking a sum of the HFCS power to drive itself and drive aircraft systems. But also things like we've got no vacuum to drive vacuum-driven instruments. So that's not been too difficult, but we've had to replace a couple of the basic flying instruments with electrically driven instruments instead of vacuum-driven, but they're off the shelf, so that's not as hard as we first feared. And then packaging is very challenging. So that nacelle is actually not very big for the 6-cylinder Lycoming, and we're packaging effectively a 240 kilowatt power station into there and a 220 kilowatt motor into that small nacelle. So we will expand the nacelle slightly, but we're trying to contain that expansion because we don't want to destroy the aerodynamics of the aeroplane. So, for example, that 240 kilowatt power station, we're going to fit in a package volume of 423 litres, which is really small. And you'll see hydrogen fuel cell companies have not done that before. And some of the other projects involving hydrogen fuel cells have big rack-mounted systems that go in the cabin. We can't do that. We're packaging for real. The packaging challenges are substantial. System safety is important. Partly because it's a very complicated system, and we are setting ourselves, we've got to create the safety case for the permit to fly, which will have flight limitations, and then ultimately this is going to be certifiable in discussion with the CAA. So that's been a challenge, and the certification is a challenge as well. So we've tackled that we've already applied for our permit to fly with the CAA, because you apply somewhat in advance, and we've gone through a series of briefing their experts and their panels on our system. So we can now get into discussing the flight limitations, the safety case that goes with our demonstrator. And then in parallel, we've already started the discussion about the certification of our products as an STC. And it's a case of this is all novel, so we're teaching the CAA as much as they are advising us on what they need to see. It's a collaborative effort because they're new technologies. We are finding that we think this is only meaningful when you look at it at the aircraft level. And that's where we see ourselves as aircraft integrators and think that's where the value comes. And we as Cranfield Aerospace Solutions and Project FRESSON think we differentiate ourselves from some of the other hydrogen fuel cell powered projects who are either making assertions of they'll make their fuel cell certifiable or they'll make their tank modular. It doesn't work like that at the moment. There are no individual certification standards for an electric motor yet, although it's close, or a hydrogen fuel cell system, or a fuel system, hydrogen fuel system. So the CAA is certainly saying, we don't know where to draw the boundary. There's no certification spec or TSO for a particular subsystem in it. So they are insisting on taking a whole system approach from fuel tanks to propeller. That is the propulsion system. And it can only be certified as a whole system installed in the whole aircraft. And we also find it's only optimised at aircraft level. So we've been doing very, very fine trades between things like propulsive power and heat rejection versus the power we need to overcome a cooling challenge. And those trade-offs have become more subtle as we've gone through the process. So originally the trade-off of do we have a battery or not was all about mass. Actually, there's a trade-off between battery mass and can you make the cooling challenge easier, and therefore put a bit of battery mass in there but have a bit less cooling drag. Those trade-offs are more complicated. As I say, it's only certifiable and qualified at aircraft level currently until we've got certification standards or TSOs for individual subsystems. And why do we think that's clever? I'm not going to go through the V model, so the classic systems engineering V model of requirements, development and validation, and then design and implementation and verification up the other side. I think I would suggest that with conventional systems, the left-hand side of the V is largely based on customer practice and experience. If you're designing conventional systems and subsystems going to conventional aeroplanes, this is circumvented or accelerated by experience. But this experience doesn't exist. And some of these systems we're using are automotive systems or coming from companies with automotive background like Ricardo. So we're having to do this full V model scrupulously to get to a system that we can validate we're building the right thing and then verify that we've built it right. There's no basis to circumvent that. So that's again why we think taking our whole aircraft integration approach is actually going to give us success, and some people who are looking to do it in a different manner may not have the same success. And back to the system diamond again. So in terms of it's that integration, that diamond in the middle, as I mentioned, that pulls it all together, and we're finding that's actually what's delivering the performance that we need, the mass that we need to get us within target for mass, the safety because it's a system as a whole, and therefore it's what making it certifiable, and then will lead to certification in the future. And therefore, there's some examples of what we're learning. So I mentioned the thermal management challenge, which was we have really got a problem here. So as I say, the level of heat rejected by hydrogen fuel cell is similar to a piston engine, but it's high heat, low temperature, and not rejected as exhaust gases. With that 2.5 square metre radiator, we couldn't have flown, we didn't have a solution this time last year. But now, having scanned the state of the art in terms of heat exchangers and then teamed with reaction engines, we've now got a win-win. We get the right solution we need, they get to come with us on the journey and make their technology certifiable so that it can be sold for other aviation applications. So we've solved that, and it's only by taking the approach we've done that you expose those and then solve them in a manner that's viable. Similarly, electrical architecture. So I mentioned this complicated electrical system from fuel cell stacks to motor windings. That's very heavy, that's very complicated, it generates loads of thermal and packaging problems. We've come up with some innovation in there, which I can't show you the detail of, but we've changed that process to save a huge amount of mass. So the graph on the right is our history of mass over the last few months, and last autumn, against a maximum takeoff mass of 2,994 kilos, just under 3 tonnes, we were 350 kilos over that, with a combination of the amount of electrical hardware we had to fit in there, plus other factors. So it's taught us a couple of things: is scrupulous mass management. So we now know to the nearest 100 grams the mass or predicted mass of every bit of the aeroplane, into the bits we're removing and then the new bits we're fitting. And I track that every week. We update that. So with scrupulous mass management and setting demanding targets to subsystems. But that big step down, which is, sorry, it's hidden by the icon, but to the right of, behind the RB screen on there, there's a 300 kilogram step down that goes well below the mass limit, and that was our innovation in electrical architecture. So we have a way of connecting fuel cell stacks to a motor that's innovative and different, that saves us 300 kilos, and that gives us a solid basis to give us a viable product when we do the further design iteration. And then in terms of that design iteration, to get from our 2023 demonstrators to our 2025 products, we know we're going to have to do a design step in a number of areas. So we know we're going to do some system design optimization. So I've set our engineers a 10% mass reduction target in that evolution. I think if you can't accept and achieve 10% mass reduction in the design evolution, you shouldn't be an aircraft engineer, so they can do that. In terms of basic aircraft mass reductions, our friends in Britten-Norman are looking at means to reduce the mass of the aircraft and its fittings anyway. So they've given us their plans set, and we've used it as a shop, and they said we'll have that, thank you. And that's going to save us some budget towards our product in collaboration with Britten-Norman. And we've also set our suppliers targets in terms of, and partners in terms of specific power increases. So we know where we need to be in terms of specific power for EPU, electric motor, and we've benchmarked that by talking to some of the leaders in the industry. We quote a figure, and we don't get told we're stupid. So we're setting a reasonable evolution for that in terms of motor power to weight, and also hydrogen fuel cell system. That's the heavy system, and we already, with Ricardo, our design of that subsystem, we have a quantified roadmap to get to where we need to be in terms of the identified improvements they know they can make in that next design iteration. And also we need to get the fuel tanks down to a mass, and that's That's probably the most challenging area of technology, is to get those fuel tanks down to the mass we need them to be. These tanks, because they're very high pressure with gaseous hydrogen, they're inherently extremely heavy, and it's a large part of the mass budget for the aircraft. So that's where we've got to with the demonstrator. We're to place in the project. We're going to fly a demonstrator in 2023. So we're right at the moment between preliminary design review stage and critical design review, with both the aircraft, its integration, and also the subsystems. It's part of a initial project, so it's 2023 demonstrator, 2025 products, but it's also a means to an end, because that will give us an applicable, scalable hydrogen fuel cell system that we can then apply to a larger aeroplane, either by scaling up the system or by installing more than 2 systems in a larger aircraft, and then will give us somewhere to go. It also means our approach is now, this is all so far fuel with gaseous hydrogen, because that's going to be an available fuel. But at some point we'll need to move to liquid hydrogen, because you change from the challenge or the difficulty from being a high pressure tank, which is very heavy, for gaseous hydrogen. The challenge for liquid hydrogen is one of insulation, to keep the liquid hydrogen at a low temperature and limit the boil off to gas. And volumetrically it's much more efficient. So there will be a transition eventually from gaseous hydrogen to liquid hydrogen, partly driven by size of aircraft, but also partly largely driven by availability of the fuel. So by the time we've entered market and established our track record with this gaseous fueled hydrogen fuel cell system, liquid hydrogen will have caught up in the next generation. We'll probably have liquid hydrogen fueled. And we've built a real solid foundation for taking this forward in the future. So we've built some expertise in zero emissions propulsion, and this is truly zero emissions. So that when this flies as a demonstrator, it doesn't fly with a conventional engine on it at all. It's flying its first flight fully hydrogen fueled. We've created a capabilities intelligent customer, working with our partners and suppliers in that consortium I've mentioned, and we're developing unique intellectual property in our novel electrical architecture that saved us all that mass, in propulsion systems installation design, and even things like design guidelines and rules. So how do you route a hydrogen pipe? What's the right bore for a hydrogen pipe? What's the segregation you need between a 1000 volt DC high voltage electrical cable and a 350 bar hydrogen pipe work? Those design rules don't exist. But design rules like that are the lifeblood and the real value of the established airframers, and we'll have that book of how to design the hydrogen aircraft before most other people. So we will develop this, and then we'll go further, because we can see this will get us to market, but the true potential of the hydrogen fuel cell powered electric propulsion system comes when you can design an aeroplane around it as well, so it's fully optimised for that. And that's actually where we coming towards one of my last slides now, is in terms of our roadmap. So this will all be about FRESSON phase 1, which is the hydrogen fuel cell powered electric propulsion system for the 9-seat Islander, demonstrated next year, product in 2025. Gaseous, that allow us to solve the problems, the fundamental problems, develop the expertise in that form of propulsion, and also give us a marketable product. Following on from that, we're going to apply that technology, scale it and modularise it to fit into a larger aircraft, so something of a class of 19 passenger. So something like a Twin Otter or a Cessna Caravan, but not necessarily either of those. We haven't selected yet. These all have their advantages and disadvantages. But effectively, take what we've learnt with the Islander, apply it to a larger aeroplane, which is a different and larger market. It's FRESSON phase 2. And we're at the stage at the moment where we're gathering and developing those top-level aircraft requirements for that next phase for FRESSON 2. FRESSON 3 is when we start getting really ambitious, and we take our proven propulsion system that we've proven in the 9 and 19 passenger applications, and we design a new aeroplane around it, because that's when you really get the benefit of the propulsion system. Rather than fitting the 21st century propulsion system into a 20th century aeroplane, we do that. And our chief executive likes to say, you just design an aeroplane around it. That's easy, isn't it? Okay. So we get ambitious then, and that may well be with partners to do it, because we see ourselves as an airframe and integrator. And then beyond that, to apply it to a larger aeroplane. When we get to that larger aeroplane, by that time the cut-off between, is it hydrogen fuel cell systems or is it hydrogen combustion? It's almost certainly liquid at that stage. So this is a multi-year strategy for the company and for zero emissions propulsion. But FRESSON is the first step. So that was my last slide, and that's what I've covered. So mentioning Cranfield Aerospace Solutions and where we've been, but where we see ourselves as an airframe integrator for zero emission propulsion. The FRESSON mission is to bring the world's first certified, truly green passenger carrying services with the products being in service in 2025. The team is part government funded to demonstrator, but it's largely private venture and will be private venture funded to product. And it's us with a really strong team with people like Ricardo, Reaction Engines, Innovatus, Britten-Norman and Cranfield University. Explain the aircraft for FRESSON 1, which is the Islander, because it's the right size of aeroplane, it's the right market opportunity for us. And why hydrogen? Because it's the only way you get truly zero emissions flight with a good business case behind it, a very strong business case actually for operators. The concept is quite simple. We get rid of the piston engines and their associated fuel system and replace it with a hydrogen fuel cell system in each nacelle as the power station, providing the electric power to the motors to drive the propellers. And then it's all about the aircraft level integration is where we think the real value is coming and the learning we're getting from that and what we're going to apply to the larger systems. And that's part of a roadmap that takes us 9-seat, then 19-seat retrofits, and then 19 passenger new build and then something larger. And that's my last slide and an opportunity for questions.
Thank you.